Okay, so let us solve the 11th exercise. We have already seen what it asks from us, so we move straight away to the solution. Note that in the first part, we have to prove that the new system is a ring, that is R tilt is a ring. R tilt, if you recall from the previous video, it is nothing but R. The underlying sets are same, but the operations are now different. And we also have to show in the next part, we also have to figure out the zero element in R tilt. So these two things we will do together. So parts A and B. Let us consider three elements A, B and C. Okay. We are considering any three elements because we will need to show associative law. That's why we considered three elements. Now we have the first thing to notice is that the operation class makes R tilt closed. Or since we are going to figure things out about R tilt, let me just write R tilt. It just simply means that the set is R. Okay. Since the ring is going to be new, so we are using a new symbol. This is A plus B plus 1. And this belongs to R because the elements A, B, 1, they are in R. So their sum is again in R. R is already a ring. And A plus B is equal to A plus B plus 1. This can also be written as B plus A plus 1, which is equal to B plus A. Why? Because the addition in R is commutative, that we already know. So that's why we can do this thing. So it turns out that the new addition is also commutative. And now we verify that addition is associative. So this is equal to A plus B plus 1 plus C and this becomes A plus B plus 1 plus C plus 1. Using the fact that addition in R is commutative and associative, we can write this expression like this: A plus B plus C plus 1 plus 1, and this becomes A plus B plus C plus 1, that is equal to A plus B plus C. So addition has also been shown to be associative. Now next we figure out the additive identity. That ultimately is going to be the zero element in the ring. Note that A plus minus 1, this is equal to minus 1 plus A, which is minus 1 plus A plus 1, which is equal to A. Okay, what is minus 1? 1 is the unit element in R, so minus 1 is the additive inverse of 1 in R, which exists because R is a ring. And A plus minus 1 is equal to minus 1 plus A because we have already proved that the new addition is commutative. And so what have we got? By adding minus 1 to A, we are getting A back. So that means minus 1 is the additive identity, which is going to be the zero element in the ring R tilt. Also, like that, we will now write an inverse of the element A with respect to this operation, which will turn out to be nothing but minus A minus 1 minus 1. minus 1 plus a. So this becomes plus 1 and this gives me minus 1, which is the additive identity. So hence R tilde is an abelian group under this operation. Okay. So the next thing we have to check is the axioms involving multiplication, and the last one involving both the operations, the distributive laws. Right. Next, the first property that R is closed with respect to this new multiplication is almost trivial. This is nothing but a plus b plus ab, and this definitely belongs to R because this expression involves elements of R and the addition and multiplication that are available in R. So this belongs to R. Then okay, now we need to show that just like addition is commutative, associative, multiplication also has to be shown to be associative. So a dot b dot c becomes what? A plus b plus ab dot c. So when we multiply two elements, what is the result? We add them up, and with that we also add their product. So now the two elements are this and c. So we add them up, which means a plus b plus ab plus c plus we take their product. Product where? Product in the ring R. A plus b plus ab times c. So this becomes a plus b plus ab plus c plus AC plus BC plus ABC. Note that in writing the product ABC, we are not using any bracket. We are not writing AB times C. We can do that because multiplication in the original ring R is associative. So whatever way we bracket a product like that, the result is going to be the same. Okay. Now okay, we just let it sit like this, and on this is one thing, and we also simultaneously calculate the other product, and then we will see whether they are equal or not. That is much easier than trying to figure out a dot b dot c from here. Okay, so this is a dot b plus c plus bc, and this is equal to a plus b plus c plus bc plus a times b plus c plus bc. So this gives us a plus b plus c plus bc plus ab plus ac plus abc. So are we getting the same thing? You see, in these terms, first of all we have single terms a, b and c. Here also we have a, b and c. Then we have two terms taken out of three, ab, ac and bc. AB, AC and BC, and lastly we have ABC. So they are actually equal. Hence A dot B dot C is equal to A dot B dot C. So the multiplication is associative. We then have to verify the distributive laws also. Moreover, A dot B plus C is equal to what? A dot B plus C plus 1. This is A plus B plus C plus 1 plus A times B plus C plus 1. So this gives us A plus B plus C plus 1 plus AB plus AC plus A. Okay. On the other hand, A dot B plus A dot C gives us A plus B plus AB plus A plus C plus AC, and this equals A plus, have I made a mistake here somewhere? A plus B plus C plus 1 plus AB, no, it's okay. Okay. So A plus B plus AB plus A plus C plus AC plus 1, according to the definition of this new addition. Now here also we see whether they are equal. A, B, C, A, B, C. There is an extra A. Okay, and AB, AC 1. AB, AC 1. Yes, they are equal. That is A dot B plus C is equal to A dot B plus A dot C. Similarly, we are not going to verify the other distributive law. This is the left distributive law. Similarly, you can verify that the right distributive law is also true, which I leave to you, and please do that. A plus B dot C equals A dot C plus B dot C. Now we can conclude. Hence, R tilde is a ring with addition plus and multiplication dot. Its zero element, because we have to answer part B also, so this is part A. Its zero element is -1. Okay, so this is one thing. And now next we have to see what is the unit element. So apparently this ring also has a unit element, just like the original ring. This ring also has a unit element. So we now have to figure that out. Okay, so this is part C. Note that A dot 0 is equal to Okay, don't make the mistake of thinking that this is 0. This is going to be 0, because now the 0 element is not 0. This is the 0 element of R. The 0 element of R tilde is -1. So we are multiplying this 0 element of R with A according to the new multiplication, and with respect to the new multiplication, what is 0 element, no one knows. It is just an element. But now we will see that it will actually act as the unit element. So you see, this is equal to A plus 0 plus A0, which is nothing but A. Just like that, 0 dot A is 0 plus A plus 0A, this is also equal to 0. Hence, the unit element of R tilde is 0. See how strange this is. It's like things have got shifted, although we can't say like that, because the original ring is also a general ring. 0 is the 0 element in the original ring, unit element is the unit element. In our ring, in the new ring, -1 is the 0 element and 0 is the unit element. Okay. And finally, we have to prove that the two rings are actually isomorphic. So ring theoretically they are one and the same. And the isomorphism is this. Define a map F from R into R tilde, where f of A is defined to be equal to A minus 1. This is a well defined map, because if you take any element A from R, then A minus 1 is a unique element in R tilde. Element wise there is no problem, right? For A comma B belonging to R, we have now, so first of all, now we have to verify that this particular function f is a ring homomorphism. Then we need to show that it's an isomorphism and it's onto. That will tell us that it's an onto isomorphism, and hence these two rings are isomorphic. So we have f of A plus B, this equals A plus B minus 1. Okay, now how can we write this? A minus 1 plus B minus 1 plus, okay, A minus 1, look at this, plus B minus 1 plus 1. Are these two things equal? Because minus 1 and plus 1 cancel out each other and we are left with A plus B minus 1. So this is okay. And this equals, according to our definition of addition in the new ring, A minus 1 plus B minus 1. So this is FA plus FB. So F actually respects addition. It turns the addition in the ring into the addition in the ring R into the addition in the ring R tilde. And a similar thing should happen to multiplication also. Let's see. AB minus 1. Okay. A minus 1 plus B minus 1 plus A minus 1 times B minus 1. What is it going to be equal to this? Let's see quickly. This actually becomes A minus 1 plus B minus 1 plus AB minus A minus B plus 1. A minus 1 plus, okay. So these two cancel out. A and B cancel out, so we are left with AB minus 1. Yes, this is correct. Now this becomes what? A minus 1 dot B minus 1, the new multiplication, and that is nothing but FA dot FB. So F is a homomorphism Now, what is the kernel of F? Let A we have already taken, A, B, C, these things we have taken. So, let us take X. Let X belong to the kernel of F. Then X minus 1 is equal to F of X is equal to the 0 element, but 0 element of what? Since F is a function from R into R tilde, we need the 0 element of R tilde, which we know is minus 1, which implies which implies X is equal to 0. Thus, the kernel of F consists of only the 0 element in R, which says that the function F is 1 to 1. Thus, F is 1 to 1 or injective, same thing. Finally, for any B belonging to R prime, we have B plus 1 belonging to R such that F of B plus 1 is equal to B plus 1 minus 1 is equal to B. Hence, F is onto. So, F is 1 to 1 onto and a homomorphism. That's why R and R prime are isomorphic. Thus, R is R isomorphic to R tilde. I said R prime, sorry. And this completes the solution. So you see that just subtracting 1 from all the elements of a ring with unit element gives us a ring where the addition and multiplication are somewhat different, actually a lot different than the original operations. But the ring that we end up with, it again is just like the previous ring because they are isomorphic. Okay, so we don't get anything new, right? So let us now look at the 12th one. And there is a star. This one is difficult. In example, (316), we discussed the ring of two by two rational matrices. See, it may seem, looking at this language, that the matrices are rational. Don't think like that. Matrix is not rational. Rational matrices means the entries of the matrix are rational numbers. That's all. 2 by 2 rational matrices. Prove that this ring has no ideal other than 0 and itself, no ideal other than the 0 ideal and itself. So we are now given a non-commutative ring, a matrix ring, in which we have to show that the only two ideals are the trivial ideals. Okay. Although the solution is not straightforward, but it's not very difficult also. You just have to figure out what to do. Okay, then you will get it. You play around with some matrices and eventually you get the solution. It's not unduly difficult. Okay, so let U be one more comment about Herstein's exercises marked with an asterisk. If you see a single asterisk, it means that the solution will not immediately come to you. But if you think about it for some time, for some days, or even for some months, it may come to you. However, there are Herstein's problems which are marked with 2 asterisks. In fact, the next one has one such part. In order to be able to solve those type of exercises, you will need some original idea. Most often an idea that is coming from outside of algebra, something original. Okay, and most often those exercises are, it's very rare to be able to solve such things. Anyway, we will see how far we can go. So let us now solve this one. Let U be an ideal of the ring. Since we haven't given the ring any name, so we will just say the ring, because we are talking about this particular ring, the ring of all 2 by 2 matrices with rational entries. This be an ideal of the ring that is different from the 0 ideal. Okay. Now we are going to choose a matrix. Choose a non-zero matrix. So we are choosing a non-zero matrix in U. This we can do because according to our assumption, U now is not equal to the 0 ideal. So there is at least one non-zero element that we have chosen. Now what can we do with this? Now there are some calculations. I will just copy from here. Note that the following matrices are all in U. What matrices? B A D C, which is equal to A, B, C, D times 0, 1, 1, 0. You can verify these calculations. CDAB equals 0, 1, 1, 0 ABCD. Then D 0, 0, 0. This equals 0, 1, 0, 0 ABCD, and then there is one more 0, 0, 1, 0. Let us first see what we are saying here. We have taken an element ABCD in the ideal U, which is a 2 by 2 matrix, and this element is non-zero. I mean, this matrix is non-zero. All the entries are not simultaneously zero. At least one entry is non-zero. Now, if I multiply this element from U by these matrices, then all these products, these three products will belong to U. Why? Because U is an ideal. So if I multiply any element of U by arbitrary ring elements, either from left or from right or from both sides, the result is going to give me elements in U again, because U is an ideal. That's why we have written, note that the following matrices are all in U. Okay, but what is the advantage of doing these calculations? You see, there are four cases, right? Our ABCD, this matrix is non-zero, is not equal to the zero matrix. That means either A is non-zero, or B is non-zero, or C is non-zero, or D is non-zero. If A is non-zero, then we consider this element in U. If B is non-zero, then we can consider this element in U. If C is non-zero, we can consider this element in U. If D is non-zero, we can consider this element in U. Now note this thing. These elements in U can always be found, and I mean, what I am trying to say is that we can always find a matrix in U where the first row, first column entry is non-zero, because in these cases, instead of taking this one, I can take this one or this one or this one. So in any case, I will always find a non-zero matrix in U where the first row, first column entry is non-zero. Okay, so that's why I write next. So we can assume too much mosquito. We can assume, yeah, too much mosquito, not too many mosquitoes, because it's uncountable. So we can assume A is not equal to 0 without losing generality. Okay, so at once I can consider a matrix where the first row, first column entry is non-zero. Now, the following two matrices are in U. Again we are going to carry out some similar calculations like these ones. And what are those calculations? 0 0 0 1. This is equal to 0 0 1 0 A B C D 0 1 by A 0 0. Note that this matrix exists, it makes sense because A is non-zero. So 1 by A is a rational number. So here we are again multiplying this ideal element by these two arbitrary elements in our ring. So the product will belong to U. And just like that, this matrix also 1 0 0 0 will belong to U, and this equals, this is coming from this product 1 by A 0 0